Good evening, everyone. Welcome to our 8th talk of the term. We have with us today Professor Abe Lee. He is the Quinn Professor of Physics at UCL and Director of the Department of Synchrotron Radiation and Nanotechnology at the Paul Scherrer Institute. He is also a professor at ETH Zurich and EPFL. He was the co-founder of the London Centre for Nanotechnology, and he was director there for quite a while. And so we're looking forward to his talk today on the next life of silicon.
Thank you very much for coming to this talk at the end of the term, even when you have to study hard for the exams or whatever. I would obviously like you to interrupt me if you have questions, because it's not much fun to sit through a talk where you're not following. But this is the topic. It's the next life of silicon. Let me just see if I guess I have to. Just let you know that the work I'm going to talk about has involved many people, both in London, but also up in Scotland and in Europe and even the U.S. There are some papers here that are listed. You might want to look those up if you have an idle moment. Let me just start off by reminding you of something you already know. I mean, these are the devices that we love and cherish and have really become part of our daily lives over the last decade or two. And of course, they represent sort of the end point or the current status of a very long evolution, which goes under the sort of rubric of Moore's Law. Just to remind you of what that is Moore's Law describes probably humanity's biggest technical achievement. What's shown here on the vertical axis is the calculations that you could perform per second per $1,000 from 1900 to the present day. You notice this is a log scale here. This is a linear scale. And this log scale here covers, this is down here 10 to the minus 10, this is 10 to the 15, there's 25 decades there. And what's interesting, of course, you know that if actually our ability to compute expressed in this way, calculations per second per $1,000, were going up simply exponentially, this would be a straight line on that plot. But actually, this growth of information processing capability is actually follows, if you plot it over this length of time, is actually super exponential. And it's pretty interesting also that this super exponential law, of course, has crossed what are called different technology nodes. I mean, 120 years ago, we had electromechanical computing devices, and those essentially were operating for about 35 years. Then we had relays, then we had vacuum tubes. Then we had individual transistors, and then for the last, actually, very long time now, almost 50 years, we've had the integrated circuit. And what's happened is actually the pace of technological progress has actually been increasing just when measured on this semi-log plot. And it's gone across these different technology nodes. And this is, of course, a kind of device that your great-grandparents are working with here in 1900. This is what you're working with today. Just to put this in perspective, this is amazing. So 20 orders of magnitude improvement in technological ability. The only thing that comes close to that kind of rate of improvement, and probably the other sort of achievement as a species, again, we're probably most proud of, is air travel. And air travel actually, for the first 30 years or so, grew also as quickly as computation. This is Kitty Hawk in 1903. And these are the Wright brothers, and one of them Orville, convinced Wilbur to sit on this biplane. And it actually barely took off. It only flew 12 seconds, and it did that just for 3.5 meters or so, and then before it crashed again. And so that's what they were doing with powered flight in 1903. And actually within 30 years, people were flying these boats around, 30 people easily. And they were flying at 25 kilometers per hour, and actually, if they had a lot of fuel, they could actually even fly a long distance, fairly long distances without refueling. That was a huge advance, and in fact, if you look at that on a log scale, it's similar to the rate of improvement of information technology. Now, after that, actually, not much has happened. You've probably seen these at Heathrow. This is the biggest plane we have today. It's the A380. Lots of airlines fly it. On a log scale, actually, this is not terribly different from that. And so, information technology really is very special in that it's kept going. And it's kept going as we've changed technologies. I mean, here we just changed technologies from propeller to jet. We've got some fancy wings and so on, but it's not really come that far. Just to put a fine point on it, if flight had improved as much as information technology over these last basically 80 years, you'd now be flying between London and New York in less than a minute with 1 million people on board. And of course, you're physicists, so you know that this is physically possible because this 1 million kilometers per hour is still a lot less than the speed of light. Of course, there's some problem with the luggage retrieval and the in-flight meal service, but those are practical problems for the the engineering community to solve because again, there's no physical limit there. So that is how well we've done with data processing over the last 100 years. Now, why have we done so well? And especially why have we done so well over the last 50 years? The reason we've done so well is this device here, which is the original transistor, which was built in 1947 at Bell Laboratories in New Jersey in the US. This thing is about 30 centimeters tall. It looks like an arrowhead, which in some sense it is. This is just a junction between two hunks of germanium. This was about 30 centimeters tall. This object we've been able to miniaturize just with relentless regularity. So over the last 60 years, we've come from this single junction device to putting literally billions of transistors together in integrated circuits the size of your thumbnail. And the reason that we've been able to do that is because we've simplified the transistor to the point where it actually looks like this. This is the simple field effect transistor, and its basic components are, of course, there's a silicon substrate wafer, and then there's something just called appropriately a source and a drain. And if you think of a plumbing analogy, there's a gate on top. And depending on what the voltage is on this gate, the channel between the source and drain is either open, which is the case here for the on state, or closed in the off state. And what we've been able to do over the last 50 years is make these devices ever smaller because they're simple planar devices, and the size scale that we have is simply fixed for our ability to do lithography. In other words, to paint these structures on top of silicon surfaces. So what's happened is using essentially mainly optical lithography, we've just simply shortened the wavelengths. We've learned about all kinds of photoresists and evaporation processes, all kinds of basic material science, and we've been able to simply constantly reduce the feature sizes and therefore pack more and more transistors onto the area of the typical chip. Just to show you the driver, this is simply the minimum feature size of microprocessors as a function of time. It's projected out to 2020, so we're sitting around right here. In 1970, it was considered pretty good to have feature sizes of 10 microns, and we're hitting now, as we go towards 2025, we're headed towards the order of 10 nanometers. Of course, as you know, you have to square these numbers and invert them to get the kinds of densities. So the performance improvements, of course, that you would see typically scale is, I guess, the square of this quantity here, not just linearly the quantity. So you can then easily see how many orders of magnitude of improvement could be derived from these improvements in photolithography. So this is the picture of information technology and what drives it, and what has been driving it essentially since we moved from single sort of transistor devices in individual cans 60 years ago to today's integrated circuit. If you look at these plots, it looks like we're just going to continue to benefit from continuous improvements in integrated circuits going into the future, because we could envision that we could just keep going down here to a nanometer and maybe an angstrom later on. Now, that may be true, and in fact, that's what the semiconductor industry thinks will happen, or hopes will happen, but there are several problems with this paradigm, this transistor paradigm, this MOSFET paradigm I just described to you. And let me just show you a few. Here's the first problem. Obviously, as you decrease the as you increase the density of switches, actually the power density, not surprisingly, goes up. And so the power density actually here is plotted as a function of the minimum integrated circuit feature size, going now from large to small here. Okay, so this is 22 nanometers down here, which is where we're headed in 2020. And basically, we've long ago actually passed the point where the power density in a typical IC is comparable to hot plate or panini oven. Actually, where we're headed towards is power densities, at least local power densities over very small areas on integrated circuits, are headed towards the kinds of temperatures you find at rocket nozzles or surfaces, the surface of stars such as our sun. So we have a potential thermodynamic problem that as we pack more and more of these switches together, the density of power goes up to the point where actually you might melt the silicon. So that's one problem that's showing up. Now another problem that's showing up is economic. Of course, it's true that the cost over time per unit transistor has been trending down. So now you can buy a lot more transistors for $1 than you were able to buy 10, 20 years ago. However, if you look at so what that means is, of course, that the facility cost per unit output, that means per transistor, in other words, the portion of each transistor that you have that's attributed to the capital cost of buying the fabrication plant, that's been trending down according to this blue curve. At the same time, though, the bet that a manufacturer has to make for building a fab has been going up exponentially with time. And in fact, these are the green curves here. And this is what a typical, if you read the newspaper, you see what Samsung or Intel are spending. Every 6 months there's some announcement that one of these companies is going to build another big fab line in Korea or somewhere in Oregon in the States or in Taiwan. That facility cost, though, has been growing exponentially. Around 1970, for $10 million, you could get into the semiconductor business. Nowadays, we're headed towards $10 billion fab lines. And so what that means is that if you extrapolate that to 2020, you're talking about fab lines which are going to cost $100 billion. There's very, very few things that we can imagine making bets on that cost $100 billion or even $1 trillion, which would be 10 years after that. And the reason that these capital costs are going up is, of course, that as the feature size shrinks, you have to actually buy ever bigger and bigger microscopes, as it were, to actually produce the integrated circuits with those feature sizes, with that density of feature sizes. You know that if you go to the Cavendish, an electron microscope is a much bigger and more expensive thing, electron microscope and see atoms, than an optical microscope. Optical microscope sits on a bench, it's quite cheap, you can get nice ones for 50,000 pounds. But electron microscope, which can see feature sizes of nanometers, it was going to cost you £2 million. And so as we've been shrinking the feature sizes, actually the machines that produce these integrated circuits with those feature sizes are getting bigger and more expensive. And that's what's driving this cost. So eventually nobody may be willing anymore to take the risk with the next generation of chips, essentially to make them. So that's economics. And now let me go to physics. So I have thermodynamics, economics, and now physics. These are now just experimental devices, but it shows a trend nonetheless. This is going from 1988, more or less to the present day. These are electrons that are switched per device per clock cycle. And so when I have that MOSFET I showed you at the beginning, there's a certain number of electrons that are switched within each clock cycles. Clock cycles, as you know, are measured in inverse gigahertz, or sort of nanoseconds typically. And how many electrons do you need to switch to have a meaningful event setting your essentially your transistor to be either on or off? And this has been marching down, of course. So as the devices get smaller and faster, you're switching fewer and fewer electrons. And of course, if you extrapolate this trend, actually, you're sort of switching single electrons around this time. Now, you know the electron is indivisible. And so we just simply can't get any further down this curve. So there's a real physical limitation to this normal classical computing paradigm where we essentially say at the end of the day that the switch is on if an electron is there and it's off if one electron is not there. Just one electron is essentially the unit, the fundamental bit. Not 10,000 as it was here, but just one. We can't get any smaller than that. And so this means that we might actually see the end of Moore's law for the current type of technology we have. And let me just review what we've had. So we've got more and more risk because we've got escalating design and manufacturing costs for successive generations of ICs. The other thing I showed you was this heat death. Of course, ever larger packing densities, ever thinner gate oxides, larger leakage currents, larger power consumption. And at the end, of course, if we just keep going, and if we wanted to take advantage of the type of performance we can have with smaller devices, we have to switch less than one electron per operation. We know that that's not physically possible. Of course, there's this general question is, if you just have one spare electron, can that even be stable for data storage and computation? So that gives us a set of challenges, and I think these are the challenges that only physicists actually can meet, because we're trying to invent new principles to actually go to the next node on that Moore's law that I showed you. Remember, I showed you how Moore's law crossed over from electromechanical things to vacuum tubes to single transistor to integrated circuits. We're looking for something similar to that switch that we did, let's say, between vacuum tubes and transistors. And we want to do that essentially by, there's two ways we can continue this process. One is we could actually follow the semiconductor industry roadmap, which has ways, to improve the current technology incrementally. But what we really want to do is go around the physical limits set by the extrapolation of the current paradigms. And there's two parts, of course, to the current paradigm. One part of the current paradigm is the transistor itself. The other part of the paradigm for computing we have is, of course, the von Neumann-Turing paradigm, which is the whole concept of a digital store program computer, which I'm assuming, even though you're physicists, you've heard about, that if you understand what's actually going on inside here is there's a set of instructions which are also zeros and ones, which are just as changeable as the data, but it's basically you're always operating on strings of zeros and one, and actually doing it in series. You could then eventually run parallel processes, but at the end of the day, you're just manipulating zeros and ones. which is what you're doing today. You really want to move to those are the twin paradigms, and those are the paradigms that have locked us essentially to these kinds of digital circuits for so long. But if you view the limitations that I've shown you, maybe we want to change paradigm, and of course then keep going on that Moore's law super exponential plot I showed you at the beginning. So new types of computing. So there's many inspirations that one can have, especially these days also for biology. This just puts biology in perspective a bit. This is a transistor for just a 90 nanometer process. It's a pretty stupid device. This is essentially just a source and drain. There's a gate there. And this is either on or off. This is an object which is the same size. It's an influenza virus. This thing here is a much more complicated machine than that, and it packs it all, of course, into the same volume. And so one can take inspiration from biology and think that, well, there's a lot more information that's stored here than there. This is not just zeros and ones. This is a whole lot of. There's a whole genome here for this thing. There's a genetic code. There's lots of amino acids, lots of nucleic acids, and that form the basically genetic underpinning for this, as well as, of course, all the proteins in there, which are amino acid sequences. There's a lot of information, and then this thing can replicate itself and make you very ill. So there's a lot there. In biology, of course, there's also neuroscience. We're trying to understand the brain. The brain is remarkably good at processing information with actually very, very low power. The brain is essentially just operates, at power levels that are less than your typical laptop. Yet it can do quite a few things that your laptop can't. Of course, there are things that your laptop can do that your brain can't do. But there's inspiration there as well. But this is a physics seminar, so I'm going to talk about what happens when we replace the sort of classical information, which is really related to whether a charge is there or not, or whether a switch is on or off. We're going to replace those bits, those digital binary bits, with quantum bits. Those quantum bits, of course, as you know, are now no longer discrete entities. The quantum bits, of course, inhabit a Hilbert space. And if I just have simple, how to generalize essentially these simple binary bits to that whole Hilbert space, is I just think that of these two bits here as vectors, as essentially, if you wish, as just, let's say, vectors in a, let's say this is represented essentially by a vector standing up here. And this is essentially a vector standing down. And then I can create essentially coherent superpositions of all of these by moving into this Hilbert space, which just lives on the unit sphere. Okay? And so states are now essentially just labeled by points on the sphere, which then correspond to superpositions of up and down with complex coefficients out front. And of course, the reason that they live on the unit sphere, you've probably all heard about the normalization condition on wave functions in your quantum mechanics course. Of course, the reason they're on the unit sphere is precisely that wave function normalization condition. Okay? So that's what we're doing now. And of course, you immediately see that that you have tremendous information potential. Now, if you have a single electron, which is somewhat a quantum mechanical object rather than a classical object, you have these two angles, longitude and latitude. It's a sphere, right? So it's just like the Earth. Every point on the Earth is represented by longitude and latitude. So suddenly you have a whole vector space to play with rather than simply a choice between 0 and 1. So the information density has just gone up, essentially as much as the density of points that you can measure on a sphere. Okay. So where you used to store just 0, 1, you can store all this stuff. So there's enormous information potential, because where we had a single classical state before, we've got a whole vector space. The other thing, of course, is that you've probably heard about is that, of course, the quantum dynamics is governed by some kind of a Heisenberg equation of motion. And if you have a whole bunch of these vector spaces interacting, there's this property called entanglement, which actually provides a natural parallelism for computation. So typically, operators scramble up the different coefficients of the different prefactors here in this expansion of the wave function, and that means different bits of the vector space evolve in different ways, and that is essentially giving you this property called entanglement, and it provides a natural parallelism for the calculation. And exploiting entanglement is really a major goal of quantum information processing. Now, the problem with all of this is that, as you know, you've probably learned the Heisenberg uncertainty principle is that quantum states are actually quite fragile. In fact, if you know what the state is, then essentially, if you know one aspect of the state, let's say you're dealing with a simple particle, you can really only know either its momentum or its position. You really can't know both at the same time with any degree of precision at all. And in fact, if you look at them, if you get an answer, if you read out the state of a quantum system, essentially you destroy that quantum state. And so this means that it's actually extremely hard to think of a case where you can essentially store quantum information, which means not touching the system, and at the same time try to manipulate quantum information, or much worse, read it out. So this puzzle of how do we exploit quantum states for computation has kept physicists busy, for the last, essentially for the last 20, 25 years. Of course, at the philosophical level, this has kept actually kept people like Einstein and Bohr worrying for the last 100 years, since it's actually the invention of quantum mechanics. But in the last 30 years, because of this perspective and the Moore's law, people have become interested in these issues, not just as a philosophical matter, but also as a practical matter. So, what have people been doing at the practical level over the last 10, 20 years? Well, some people have been winning Nobel Prizes, especially atomic physicists. These are actually some lovely images from Wineland's group, where these are actually pictures of single atoms in prepared quantum states, and actually single atoms, pairs of atoms, and so on, where they're actually able to set the wave functions of atoms that have been trapped in vacuum. So stainless steel pots with typically with some electromagnetic confining fields just applied on the outside of those pots, and then some lasers essentially to tune up the wave functions. Now that's all very nice. That's of course extremely unlikely ever to wind up in your laptop. So people in material science and solid state physics have worried about trying to do those kinds of tricks in solids. And of course, there are many competing technologies there. Very popular recently have been superconducting qubits, so you can make superconducting circuits. Superconductors are intrinsically quantum mechanical, and they can be set up in such a way so that some of their, as it were, degrees of freedom behave in a quantum mechanical way, which is can be directly represented in terms of this Bloch sphere that I showed you at the beginning of the talk. People have also made various devices based on semiconductors, fairly conventional semiconductors. There are other people trying to treat the spins in individual, what are so-called molecular magnets. Those are just it's like tiny magnets. The magnets are small enough they really behave quantum mechanically rather than classically, and trying to exploit that property of magnets. They've exploited various defects in diamond. There's just a whole host of attempts to try to get viable quantum mechanical bits in solids, bits that would be as viable as essentially free atoms are in traps. The problem with all of these things is these materials and systems is that they're fairly exotic. And in fact, what we'd like to do is have a common solid, which we really know how to process. Okay, so we've already spent all this money on these fab lines, and we spent all this money on research for the last 50 years, and we'd like to use that solid essentially to then host quantum bits rather than just classical bits. And of course, the solid I'm talking about is silicon. So let me just remind you a few things about silicon. Silicon, of course, is here on the periodic table. It's pretty light. It's element 14. It's extremely common, actually. It's, in contrast to diamond or molecular magnets, constitutes slightly more than a quarter of the Earth's crust. It, of course, appears on other planets, so it's quite likely that if there's intelligent life out there somewhere else, they would have also be using it for information processing and maybe to communicate with us one day. So this is silicon, and it forms, of course, in this famous diamond-like lattice, just cubic. You can get quite large crystals. We're getting very good at growing huge crystals of it, again, for making wafers that are then used as the substrates for our modern electronics. So the rest of the talk now, I'm going to tell you how we can actually manipulate the quantum states and actually look at the quantum states of defects actually in silicon. And we're going to look at silicon as an atom trap. So I've shown you the big periodic table. I'm just going to show you now the small piece of the periodic table near silicon to show you that actually we can realize a system in silicon which is remarkably like as just an atom in vacuum. And how do we do that? Is there anything in silicon actually that behaves like a trapped atom? Well, it turns out that I can substitute. This is column 4 of the periodic table, and you remember that the outer configuration of silicon is 3s2, 3p2. If I move to the right of it, of course, there's one more valence electron on these elements in column 5. This is column 4, so that refers to 4, of course, as there are 4 electrons, and here's this 5 valence electrons. And so if somehow I can convince phosphorus to substitute for a silicon atom in a silicon crystal, then I've got something in silicon which has essentially a spare electron. Let me just show you. So I substitute phosphorus for silicon. It's got one more p electron. And of course the other electrons are just forming essentially the same covalent bonds that we have to start out with the silicon neighbors. But there's a spare electron, which of course has got one extra charge and one spin a half. And sorry, okay. Yeah, and I'm going to write down something I hope you've seen before. This is, of course, the Hamiltonian for the hydrogen atom. You'll remember the hydrogen atom has two contributions to its energy. One is, of course, the kinetic energy term. This is just this grad squared over 2m star. And the other is a potential energy term, which is just a Coulomb interaction between the core and, in the case of the hydrogen atom, there's just a proton there, and the electron. And that just falls off as 1/r. And, of course, you know that you want to look at that Hamiltonian, you want to diagonalize it to learn about its grounded excited states. Now, what happens, of course, is now we're no longer in vacuum, we're actually in silicon. And so all actually that it turns out that you have to do to understand what this hydrogenic-like atom is doing in silicon, which is just formed from a group 5 element that you've doped into this group 4 host, is you just have to replace the free electron mass with the effective mass that's provided by the silicon medium. Of course, the silicon medium is not a vacuum anymore. There's other electrons there. But effectively, what that does is just changes the effective mass of the electrons, of the electrons that travel through that medium. And those are essentially, it's what's called the conduction band masses. If you add an extra electron to silicon, how will it move? What is its mass? How is that motion characterized? So basically, you can take your hydrogen Hamiltonian and just replace the electron mass by a mass to do with the conduction bands. And it turns out that actually electrons in silicon are lighter than electrons in vacuums. Put the 0.3 there. The other thing, of course, that you have to worry about is, again, because there are all these covalent bonds around, all these electrons that are not completely localized, is they will tend actually to screen out the Coulomb interaction. The Coulomb interaction will be weakened because there will be some slight motions of those electrons on those bonds, which will tend to shield charges from each other. And that shielding tendency is taken into account by the dielectric constant. That dielectric constant is something with order 10. Okay, so this is all of the physics you need to understand the rest of the talk. Of course, there are two famous formulas, again, that I'm sure you've seen in your quantum mechanics course. The first formula is the formula for the Bohr radius, and the second is, of course, the Rydberg energy, which is the binding energy of the electron. And you can inspect these formulas. If you look them up in the textbook, you'll see quantities like h bar and m, the mass of electron, and e squared. And you can now just essentially replace the dielectric constant of free space and the free electron mass. This is the value you get for the hydrogen atom. Of course, this is your famous 0.5 angstrom Bohr radius. Okay, this is 10 to the minus 10 meters here. Now, if I rescale this Bohr radius by the dielectric constant divided by the effective mass, I get a Bohr radius now, which is, of course, a factor of 30 bigger than what I had for the free hydrogen atom, and it's up at something like 1.8 nanometers. Just think about the physics there for a minute. Why is this atom so much bigger in silicon? The reason it's much bigger in silicon than it is in vacuum is because the potential is weaker. Because I remember I said I took that Coulomb potential and I divided it by the dielectric constant. Just to remember here what this was. I divided it by the dielectric constant, so it's a weaker potential. So the electron is more weakly bound, so I have a bigger wave function, a bigger Bohr radius, a bigger atom. And of course, because the electron is lighter, it's actually more likely to move. Okay, you always know that if lighter particles tend always to be less confined than heavier particles. That's, of course, why this radius scale is like the inverse mass, not like the mass, like the inverse mass, because it's light things like to escape from bound states more than heavy things do. And that's the physics there. So we have a bigger atom, actually very much bigger atom, 30 times bigger. The other thing, of course, at the same time, is that electron is much more weakly bound. For the same reasons that I just told you, it's much easier to take that electron away from this hydrogen atom than I am from the hydrogen atom in vacuum. So that this phosphorus atom that I've got in the silicon vacuum, is actually much more easy to ionize. And in fact, if you work out the math, or look up the formula, you see that the binding energy scales, again, like the effective mass, now upstairs, divided by the dielectric constant squared. Okay, so this is 100. So this is 300 times less bound than essentially the Rydberg energy suggests for the hydrogen atom. And so I've got essentially a hydrogen atom, which is very big in silicon, and at the same time, it's much more weakly bound. But 70 millivolts. So just to get some perspective, room temperature as you know, is of order 30 millivolts. Okay? And so 70 millivolts is still about twice room temperature. Just to show you what this really looks like, here's silicon, and those are the silicon atoms, and that shows you that wave function, the size of that wave function, just by looking at the Rydberg formulas. Okay, so how do we know? So this is all the math that I'm going to show you. Don't worry. How do we know that all this is true? Interestingly, of course, the description I just gave you was literally something that people probably could have just told you 50 or 60 years ago. It's only in the last 5 to 10 years where I could actually show you some direct experimental evidence for this picture. And that direct experimental evidence comes from actually doing scanning tunneling microscopy. And have you heard of that, scanning tunneling microscopy before? So scanning tunneling microscopy, of course, relies on quantum mechanics, also relies on the fact that the tunneling rates are exponentially dependent on the distance between the atoms between which you're doing the tunneling. And so, and also your ability then essentially to also to fabricate tips and to have piezoelectric motions, which again move with angstrom level average precision. So the idea of the STM, just for those of you who haven't known about it, is essentially you take this needle and then you can, of course, tunnel between a surface and that needle through vacuum. And there are various ways in which you can operate the microscope. One way, of course, is you can fix the voltage and you can fix the current. And then simply, you simply do is you then, of course, if you do that, you have to move the tip with a feedback loop to keep that condition fixed. So let's say if I then have, let's say I have a constraint that I want both of these things to be fixed, as I move that tip, and I don't touch the piezos, the Z piezo, of course, the tunneling current might change. So then I have to lift up the Z piezo to keep that tunneling current the same. And that's a standard classic imaging mode, and that's how I get essentially angstrom or sub-angstrom level images of single atoms on surfaces and so forth, something for which the IBM group that discovered this instrument about 30 years ago got a Nobel Prize. So that's the standard imaging mode where you just see topography. There's another mode, of course, which you can use, which is where you fix the height of the tip above the sample, and then simply move the tip around. And then of course, you no longer can fix, let's say you fix the voltage, you can no longer fix the current. And then what happens is you can record the current, however, though, as you move the tip across. And that tells you something about the electron density underneath the tip. So you've got your surface here, let's say it's flat. And then if there's basically some kind of a charge underneath the surface or some funny looking wave function underneath the surface, you can actually see that in this so-called constant height scan. So these are the two modes in which you can operate the microscope. And of course, this shows you can run into some trouble if you have a step here if you're running in constant height. Whereas, of course, if you're running this way, you can see the step. But a particularly interesting thing you can do as well is, of course, you can park the tip somewhere over the sample. And then you can tell locally whether you've got a metal or an insulator, because if you have metal, then essentially that junction follows some kind of ohmic characteristic. Ohm's law is just saying that the current is directly proportional to the voltage. You can also, of course, see a gap if you have an insulator, and in fact, silicon that's not doped is insulating, and you can even measure the band gap of silicon in this way. These kinds of instruments are fairly common right now. Maybe you've seen some of them here at the Cavendish. They're basically a lot of stainless steel with funny looking protrusions where you can look through this special glass and see what's going on inside. All kinds of manipulators and so on, and then it's all attached to a computer, which produces images like this. So here is actually a topographic image of doped silicon. I've doped it with bismuth, but bismuth is also a column 5 element, so putting a little bit of bismuth in silicon should do exactly the same thing that putting a bit of phosphorus in. It's just an atom there sitting there with a spare electron. And you can see here, this is just the silicon 100 at the surface, and there are nice terraces in the topography. So there's not much exciting going on here. These are just the standard terraces which you have when you prepare silicon like that. There's something very interesting, though. If you do the DIDV map, in other words, if you operate in constant height mode rather than in feedback mode with constant current, and I'm going to show you this same image that I showed you a minute ago. Here's a topography, and this is a density of states map. This is showing you where the electrons are. And there's a very funny thing that you can see here. These are completely, these are the identical XY coordinates, so they can be completely overlaid. You can discover, of course, that there's some funny things going on here near these step edges, but here there's this dot, okay? And that's at a bias voltage of minus 1.3 volts. In fact, if I go to a bias voltage of minus 1.7 volts, I also see a dot, and actually there's missing density of states here, and there's added density of states here. And in fact, what it looks like here underneath is there's a bunch of electrons. They're actually scattering the electrons that live at the surface. And in fact, the scattering center has precisely the Bohr radius that's predicted by that simple formula that we just looked at a few minutes ago. So you can actually see these objects that are predicted essentially by this very simple Bohr model of an impurity in silicon. Okay, so I've shown you that. So that means that silicon actually works just like one of these ion traps that the atomic physicists look at. So I can see that I'm going to run out of time. So I'm going to now tell you, tell you that we can actually manipulate the quantum states of these atoms using light. And then if I have some time, I'll show you we can manipulate these quantum states also using electric fields. But I'd rather that you understand what I'm saying rather than I show you too many things. But let me just talk briefly about light. So you'll remember, of course, that in addition to the ground state that you have for your Bohr atom, you, of course, also have a set of excited states, and these are the so-called Rydberg states. So this is, of course, there's 1s level, and there's 2p levels, and it goes all the way up to 3d and so on and so forth levels. And just to show you what the wave functions look like here, let's just focus on 1s and 2p levels. Here's the 1s state that I showed you before. P wave function is essentially two pancakes stacked on top of each other. The wave function here is much bigger in extent because if you look at the Rydberg formula, the spatial extent scales like the principal quantum number squared. So the principal quantum number for the 2p states, of course, is 2, not 1. But I square 2, I get 4. So this thing is 4 times bigger. So before I said the Bohr radius was essentially something like 1.8 nanometers. This thing here is almost is basically almost 8 nanometers. 8 nanometers big. That's huge, actually, and that's actually getting comparable to feature sizes in fairly conventional integrated circuits. And so the question to ask is, do you see these kinds of states? This is just a picture of some wave function. Do you actually see these kinds of excitations directly in silicon the same way you do in atomic physics? And the answer is yes, you do. And this actually shows some very old data taken at Bell Labs in the early 80s. And this just shows the optical absorption spectrum. It's the same kind of thing you do with an atomic vapor, but now the optical absorption spectrum of doped silicon for a variety of concentrations of dopants in silicon. This is phosphorus in silicon. And so here, these numbers here, this means that I have roughly 5 times 10 to the 15th atoms per cubic centimeter. Okay, so if I take the cube root of that, you can forget about the cube root of 5, but just take the cube root of 10 to the 15th. That's 10 to the 5. So you have essentially 10 to the minus 5 centimeter typical separation between these phosphorus atoms. That sort of makes sense because 10 to the minus 5 centimeters, 10 to the minus 7 meters, or if you like, 100 nanometers. So the reason you do this calculation is to make sure that that atomic picture works out, because the atomic picture will only work out if these atoms are not so close to each other that their wave functions overlap. Okay? So I want to make sure that the density is low. When that density is low, those wave functions have distinct identities, because I said those wave functions, the 1s wave function, for example, has an extent of something like 2 nanometers. The 2p has something like 8. As long as I'm below, let's say, 100 nanometers, I can start to resolve these different Rydberg lines. And sure enough, I can resolve Rydberg lines in silicon due to these impurities. And it basically looks just like, it's very similar to just looking at hydrogen vapor. What's interesting here is, of course, as I increase the density, these lines broaden out because the wave functions overlap, because of the considerations I just gave you. And of course, they overlap more for the higher lying states because their extent scales like the principal quantum number squared. Of course, eventually you get to just a big continuum, and then essentially electrons in those states are delocalized. Okay? This, in fact, these numbers here, before we did the STM measurements that I just showed you, were really the only way we knew that that Rydberg picture was roughly right. So you can tell these data are a lot older than the data I just showed you. So now, what else can we do with these states? Can we actually try to manipulate them? And I'm just going to spend a few minutes now showing how we can manipulate them with a laser. The laser we're using is a particularly convenient laser. It wouldn't be the kind of laser you have in your laptop. It's simply it's a free electron laser where essentially the gain medium is simply the electrons in a beam that's produced by an electron accelerator, and those electrons are essentially fed through what's called an undulator. I mean, they're wiggling up and down, coherently on essentially the optical wave that's produced by the emission of the same moving electrons that's also confined between two mirrors. Okay, so I have a cavity, just as I do in any normal laser. I have two mirrors at the end of it, but instead of having some gaseous medium in between, I actually have just electrons, basically electron bunches propagating in vacuum, and I get nice laser light. The nice thing about this is it's a completely tunable system because it relies only on free electrons. That's why it's called free electron laser, which means I'm not tied to any particular atomic transitions or solid state transitions as I would in a conventional laser. So it's a very flexible instrument for doing research. This is in fact just schematically what it looks like. It sits in a hall, maybe 1.5 times bigger than this, and it's just essentially will be recognizable as a miniature particle accelerator. The experiments themselves don't look much different than any conventional optical bench that you'd find at the Cavendish. Big difference, though, is because the radiation here is quite special. It's in the terahertz domain, so sort of a few of order 1/10 of a volt, and below you have a lot of atmospheric absorption lines there, which you need to avoid either by pumping out the optical bench or flowing essentially some kind of gas through that expels gases that have, atmospheric gases that have vibrational energy levels in this energy range. So pulses that we see are essentially looking like this. It's a nice thing because this machine produces essentially transform-limited micropulses, which appear in bunches. These can be tuned to be typically something like a picosecond long. And then there's separation going between 1 and 40 nanoseconds between subsequent pulses. And these are the typical wavelengths. Now, these wavelengths are in the interesting range. Before I used other units for the energy, but of course these wavelengths can be converted to energy just by the usual method of inverting them and multiplying them by the suitable physical constants. So the first experiment that we did is a simple bleaching experiment to understand what the lifetime is of these excited states. So I showed you before with the STM measurements a ground state wave function. And now I'm just going to show you an excited state wave function. And we're just going to see how long do those excited states actually live by using this pulsed free electron laser. And to do these experiments, we do what's called a bleaching. Basically, we do a bleaching experiment. The way a bleaching experiment is very simple. Works very simple. So here I have a bunch of quantum levels. And of course, what I do is I start the system off in the ground state. And let's say I'm interested in pumping up from the ground 1s state to this 2p naught state. And so I just simply come in with light with precisely the frequency which separates these two levels. Okay, it's just precisely that frequency. And then the system just sits there for a while. But eventually, that level will decay. But before it decays, I can still, of course, check to see whether it's decayed simply by coming in with a second weak pulse. So if this pulse was very strong, I've emptied the ground state and I have only excited state. What that means is that the sample, of course, to start out with, was dark at that frequency, because at that frequency, essentially there's an absorption line. If I depopulate this state, that absorption goes away. I've emptied, I know the system no longer has any occupancy of this ground state. It's all up here. If I come with precisely that frequency, this sample becomes transparent. Okay. But of course, eventually, the sample will become dark again as this state here empties back down again towards the ground state. And so if I do this absorption experiment with a weak pulse later, sample, of course, has gone from being transparent to being dark. And we can set up this optical bench. I don't want to go into details, but these are the data just showing that this all works. So this shows me the delay between the pump and the probe pulses, and this shows the probe transmission. Okay, so you see here, this is on a log scale. So this is a small number here, very small number. So the sample starts out very dark before I come with my strong pump pulse. And then I come with a strong pump pulse, and then eventually it becomes less dark first, and then eventually the sample becomes black again. If I hit it harder, the sample becomes more transparent because I'm having less and less possibility of essentially of having the transition between the ground and excited state if I put if I populated the excited state to begin with.
So,
yeah.
What's the negative delay time mean?
Negative delay time is before I hit it. I have two pulses. I have a pump pulse which is fixed. Okay. I have a probe pulse which I'm moving. So if I of course inspect the system before I pump it, the system is black. Okay, then I pump it. So I pump it up out of its ground state. Now it's got to trickle back down into it's got to trickle back from that excited state back to the ground state before the sample becomes dark again. If I whack it very hard, it gets darker, but then eventually, of course, it just restores, and it's always restored with the same one every time. So this now tells me what the lifetime is of this 2p state. So I can start doing the dynamics of these. I can populate these excited states, and I can start to think about manipulating the wave function of these impurities in the same way but these are not impurities in silicon, in the same way that atomic physicists manipulate the wave functions of atoms in vacuum. This is just for the record. This T1, this relaxation time is something like 200 picoseconds. Well, what does that mean? Well, that means I've got lifetimes near 200 picoseconds for these 10 terahertz oscillations. Of course, you know then how to calculate Q. Q of an oscillator is simply the product of the lifetime and the frequency, the underlying frequency of the excitation. And what we've got here is a Q of something like 2,000. So these Rydberg states in silicon have actually amazingly long-lived, robust, excited state wave function, in addition, of course, to the ground state Bohr atom-like wave function that we saw using STM. The implications are now that we can actually do atom trap physics in silicon. In some sense now we've had electronics in silicon, but we can now do orbitronics as well. So we can think of playing games with orbitals that we used to just play with single charges. So I think I've talked long enough. I'm just going to now just skip to the end and sort of review what I've told you today. Let me just review. The first thing that I think you want to come away with is that we will soon be at the end of the road for conventional silicon information technology. And the challenge here for physicists, rather than engineers and economists, is this plot here. Is how do we get more computational power than just zeros and ones out of the real estate on a silicon chip. And in essence, if we're thinking about switching information just as switching electrons and seeing whether they're there or they're not there as essentially the fundamental step in any kind of information processing scheme, we're really facing a problem already today. However, I believe that our data, and of course that of a lot of other people working in this area, is that we could actually move ahead with information that we process, not just using moving charges as we do in today's chips, but using static charges where we encode information using either quantum spin and the orbital degrees of freedom that those same electrons actually possess. Our view is actually that the physics, as well as new lithographic approaches that I didn't have time to tell you about today, actually make silicon look very attractive for the future. And indeed, silicon actually could have a future as brilliant, and perhaps even more brilliant than its past. 20th century, we were controlling charge. In the 21st century, which is now, it's already been going on for 15 years, we're going to move ahead by controlling spin and orbit. Thank you very much.
Can we have questions? I've got a question.
Yeah.
So, it might be a bit silly, but how do you do computation with orbitronics?
Well, I've shown you essentially that I can create, I have very long-lived orbital states. So that means now that I can start to essentially create superpositions of different orbital states. So at the beginning of the talk, I showed you how in quantum mechanics, I have a much richer state space than I do classically. Classically, I have a charge is there or it's not there. Here I can conceive of course, taking an atom, and it can be simultaneously both in a 1s and 2p state. And the precondition for being able to do that kind of orbital superposition is, of course, that I have a long-lived 2p state, not just a long-lived ground state. And so the orbital degree of freedom basically says that I can have fairly complicated wave functions that I can generate, in this case, optically, which I could then actually generate optically, and then manipulate optically And so I could essentially compute by imposing a set of operations, matrix operations, on these atoms, but I can do that using essentially laser pulses. Okay, what we do now is we do the gate operations, of course, using just small voltage pulses. But the idea here is essentially to use small voltage pulses to drive lasers, which will be much smaller than the one I showed you, to create superpositions of quantum states, and more or less actually shown in this cartoon here. You know, I'm coming in with lasers. I can control these the relative amplitudes and phases of these wave functions.
So, what's the biggest challenge? Is it the miniaturization, or is it something?
No, the miniaturization is taken care of. Just by atomic physics. Now, what's interesting is you don't want it to be too miniature, and this is one advantage of having these large Rydberg atoms. Because this is such a large object here, it means it's accessible. You can actually put electrodes here on top, which are realistically manufacturable. So the really big challenge is essentially doing the manufacturing in a way that's reasonably inexpensive, and at the same time does not destroy these quantum wave functions. Because obviously you can imagine that if I don't have a clean silicon background but a dirty background, that these states would not be so pretty and would not be living such a long time. You see that in atomic physics. If I take an atom trap and I have a vacuum leak, and all kinds of stuff comes in from the outside, then I no longer can really control the wave functions of the atoms in the trap, because there's all this other stuff flying around that produces what's called decoherence. It means that these pictures just don't apply anymore. So there's this trick somehow of fabricating, putting impurities in control locations and then having gates nearby but not too close that can then control the states. That's really the challenge. And of course, there's a lot of very nice physics to do. You know, why are you trying to meet that challenge?
That's it.
The pumping and probing graph that you showed, that was a bulk thing, I think.
That's bulk, yeah.
I mean, are you able to focus lasers on individual?
We haven't with this particular experiment. We've not focused the laser down to single atoms, but of course. The way this is done is we can get smaller and smaller sample volumes if we use electrical readout. So we can actually, what I was just saying before, these are fairly large wave functions. And so we've actually been able to show that we can read out these states electrically as well as optically. So I showed you a pump probe experiment, which is a classic transmission decay experiment. One can also, of course, look at the atoms using gates or using sources and drains. And of course, if the wave function size changes, for instance, ionization rates, which you can measure electrically, or tunneling rates, which you can measure electrically, can be seen. And of course, that can be done because these wave functions are big. Electrodes are easily manufactured on this scale. So fairly soon, I think, we should be able to demonstrate single orbital readout using electrical gates. The addressing, of course, with terahertz radiation of single orbitals is a little bit harder, but the readout is there. And of course, one can then build various structures on top of the silicon, which would essentially produce enhanced near fields, for certain impurities and suppressed near fields and other impurities. So there's a lot here one can do with Maxwell's equations, which we haven't done yet. But that's, of course, why I'm talking to you, because we're looking for people to help us do this.
You talked at the beginning about the economic challenges of silicon. How is it actually solved by using this approach? I mean, I just saw this huge laser, three electron laser, for example, and I can't really imagine having that small scale.
No, first of all, of course, that laser is used, that's used just to do the research. That's not even used to do the manufacturing. So there's two questions really. First of all, is a manufacturing, if you wanted to, you can't take that laser and put it in the laptop, that laser. However, the reason one uses that laser is simply that it's tunable. Once you know what wavelength you want to work at, then you essentially have to identify some, ideally, well, you'll find some semiconductor which lasers at that frequency. That has to be then created by design. You have to then define a particular heterostructure which has essentially that the property that it lasers at that wavelength. But the production, of course, the R&D cost to build that laser and do it reproducibly is far more than buying a free electron laser to do the research. So that's sort of the vision actually in the long run is that you'll essentially be using special purpose sources to produce exactly those frequencies, which are then somehow wafer bondable on the silicon. Now, what this does for production costs, certainly the way we're going right now, we are actually doing experiments which I didn't have a chance to show you on single atom basically dopant placement. The current paradigm that we have is certainly very, very expensive because it involves using an STM and essentially inserting impurities one at a time by hand with graduate students, which is very expensive and very slow. And to scale that up is costly. We have some ideas actually, but I doubt this is going to be much cheaper than what we're doing now. But the point is, we're getting a much bigger state space at each point than we are today. So we're getting the whole Hilbert space rather than just zeros and ones. So maybe if we could do it for the same price, then we're way ahead of the game.
Are there any more questions? Yeah, last question.
Yeah. So you mentioned that the binding energy for these atomic states is at a few kT.
Mm-hmm.
So does that mean there is a limit on the number of these states that you can put together before you assume some of them are going to be destroyed?
Yeah, I mean, the other thing that means it has to be cold.
Yeah,
It just has to be cold.
Okay.
But that's, for actually these, here you could run, 10 Kelvin, which is fairly cheap. But again, 10 Kelvin is hard to do in a laptop, but I'm pretty happy just to do it at 10 Kelvin rather than at 50 millikelvin.
Can we thank our speaker for giving us a great There'll be wine and cheese downstairs where we can take